Okay, so at this stage we got the standard model with the Lagrangian so far has three terms. There's minus f squared for the u1 minus f squared for the su2 minus quarter f squared for the su3. We put the right indices on that, and there's a sidebar id slash psi where we sum over all the guys. So, yeah, compact notation is just two terms, f squared and d slash. And d has the general form like this, is d mu plus ig1 y over 2. The convention is y over 2. The field is b mu. So this is d mu on a fermion. Plus, if it's a doublet, it has the ig2 tau dot w over 2, and for fermions there's always a 1 plus gamma 5 there, because it's only on the left guys. So, you know, you could think that could be stuck in the fermion part, but we could do that. And then there's an ig3 lambda over 2 dot the gluons. Where those guys happen if they should happen, you know, if it's the quarks. And we went through all the charge assignments on all the y's, and so it's a very funny set of charge assignments. Today we get to add the Higgs. So the next thing the last thing that we need to add here is the Higgs field, which is it's a SU2 doublet. It's a hypercharged singlet. Hypercharge has, it's not a singlet, has charge 1 plus 1. Remember, the electron had minus 1. And there's no SU3 coupling. Okay, so for this guy, the d mu on phi is d mu plus ig1 1/2 is there, b mu plus ig2 tau dot w over 2 phi. Okay, this is it's a doublet. Given that charge assignment, it's going to come out to have a positive component and a neutral component. This is going to be the regular electric charge. And so this implies really there's 4 particles. There's phi plus, phi minus, phi 0, and phi 0 bar. And there's 4 degrees of freedom. Okay. The potential is invariant, so it's mu minus mu squared phi star phi plus lambda phi star phi squared. If you wrote this if we wrote this in terms of 4 real fields, we could write this, so nomenclature, I could have written this as 1 square root of 2, 4 real fields. Let me call it sigma plus I pi 3 pi 1 plus I pi 2. Okay, there's 4 real fields. Then implies the phi star phi is 1/2 sigma squared plus pi squared. So this is exactly the sigma model. And the charge assignments are exactly the same as the sigma model also. So as far as the gauge part of the interactions is concerned, all we're doing is here's the sigma model again. Okay, so symmetry breaking, then we know the story. The story is there's a minimum at phi is 1 over the square root of 2 0 v, so it's the sigma direction. It really could be chosen any direction. They're all equivalent, but that's the one that we know and love. We will end up writing phi 1 over the square root of 2 0 v plus h e to the I tau dot pi over v. That's the same as we did for our sigma model again. I'm going to come back to that. Let's now just look at the ground state. This is the masses of the gauge bosons. Okay, so the Lagrangian is d mu phi star d mu phi, and it's v of phi. Okay, so the first piece here is d mu plus ig1 over 2 b mu plus ig2 tau dot w over 2 0 v, and then actually this is minus because it's the complex conjugate. And I wrote that badly. It's 0 v out there because it's phi star. And then we get d mu plus ig1 over 2 b mu plus ig2 tau dot w over 2 0 v. Okay. So the derivatives, of course, don't count. I just wrote them so that you carry them along. They're just acting on v at the moment. And this gives masses to various things. You can, if I break w into w plus, w minus, and wz, this comes out to be g2 v over 2 w plus W minus. Okay. That that comes from the lower components of the tau dot tau. One, and then the other pieces come out to be v squared over 8. Actually, there was a 1/2 here from this is the 1 over the square root of 2 squared. V squared over 8 is W3 B mu G1 squared, G2 squared, G1 squared minus G1 G2 G1 G2 and W3 B mu. Okay, so the G1 squared B mu is easy to see. The G2 squared comes from the tau 3 times tau 3, which is just 1. So that gives me this guy. But then there's also a piece B times tau 3 that gives a minus because it's tau 3 in the lower component, so the minus sign comes from that, and it's G1, G2. Okay, everyone see all the pieces of that? The mass matrix here has a 0 eigenvalue. You can see that because the determinant of it is 0. So if you take the determinant, you get 0. So if I take determinant of, well, if I do G2 squared minus lambda, G1 squared minus lambda minus G1 G2, if I take that determinant, this turns into minus two lambda G1 squared plus G2 squared plus lambda squared. And actually there's no 2 there. Right. Okay, so one of the eigenvalues is lambda. The other, this eigenvalue, lambda is 0. The other one is G1 squared plus G2 squared. There's an overall factor of V over 8 here, so we end up with the masses MW plus and minus is G2V over 2. Z is V over 2 G1 squared plus G2 squared 1/2. And M gamma is equal to 0. Okay, so that's the standard finding of masses from this. We define cosine theta. W is G2 over the square root of G1 squared plus G2 squared, square rooted. So that we get MW is MZ cosine theta W. that angle is also the angle that diagonalizes the masses, so that the particle definite mass are cosine theta W, W3, minus sine theta W, B, and the photon is sine theta W, cosine theta W, B. These, if I draw this angle, if this is G2, this is the square root of G1 squared plus G2 squared. This is then G1. We also have tangent of this weak angle, the Weinberg angle, is G1 over G2. Okay. So from weak decays, we'll get there. G Fermi over the square root of 2 from weak decays turns into G2 squared over 8 mw squared, which, if you look up there, is G is 1 over 2 v squared this ends up telling us that v is 246 GeV. Okay. So there's the symmetry breaking scheme. Anybody have questions about that part? Yeah. Jared.
So that V,
Yes.
is that, I mean, if you were to write that out, that has lambda and the mass of the Higgs in it?
Yeah, so the other things we get out of this, we get V is the square root of mu squared over lambda. Just like before when we did the sigma model, the mass of the Higgs turns into 2 mu squared. So that's 2 v squared times lambda. Okay, so it all hinges now on what's lambda, right? And that's the only place that lambda enters, really. Is in that Higgs potential. We haven't done it, but you can write out V of H. Let's just do it. See if I can do it from memory. It's this 2 mu squared H squared. Then there's the lambda V H cubed and lambda over 4 H to the 4th. And I'm pretty sure I have the number right there. But that's, you did it all for homework. There's this lambda V S squared and S cubed in what you're doing. And that, and then the mass term. And that's all that's left over. Okay, I mean, let's quickly do the rest of the story. So that's the bare bones story. The rest of the story of the Higgs mechanism is this business about the degrees of freedom, you know, we started off with uh, with 4 gauge bosons, which is 8 degrees of freedom, 2 helicities each. We have 4 scalars, so that's another 4 degrees of freedom. We end with 3 massive and 1 massless gauge boson, so that's 11 degrees of freedom. 3 times, no, it's 3 times 3 plus 2. And so the only thing we're allowed to end up with is the Higgs. So we have to completely get rid of the other 3. Okay? And we do it the same trick as before. If we let phi is e to the I tau dot pi over v 1 over the square root of 2 0 v plus h. That's an equivalent representation in the sense of Higgs theorem. Then d mu phi is, well, the derivative can act on the tau dot pi, which just brings it down, so let me do that. E to the I tau dot pi over v d mu plus I g2 tau dot w. Let's just keep that piece. Over 2. Then there's a piece which is I tau dot d mu pi over v. Okay. And then we do a gauge change. W a mu goes to W a mu minus 1 over GV d mu pi. And the field disappears completely. Okay, so we did this earlier in a different context, but it works here too in the SU2 context. Okay. Questions about that part? All right, so these unphysical guys turned into the longitudinal components, though there is still a remnant, which I hope to say a little bit later on when we're doing beyond the standard model physics, of the equivalence of this sigma model to the longitudinal gauge bosons, because that's one of the things that people are looking for at the LHC, is this equivalence tells us that the sigma model allows us to explain beyond the standard model physics a bit more. All right, so that's just a teaser for what we're going to do later. Interactions. Okay. this is mainly here the fermions. So we have the fermions is Lagrangian is this all these fields psi I d slash minus g1 y over 2 b mu minus g 2 over 2 tau w slash dot slashed, and for the different fields, the charge interactions are straightforward. It's L looks like W plus G over the square root of 8, W plus mu J charged mu plus Hermitian conjugate W minus and at this stage this looks like J charged is nu bar gamma mu 1 plus gamma 5. It's only the left pieces E plus u bar gamma mu 1 plus gamma 5 D plus dot dot dot. Okay. These guys at the moment are whatever the fields live in the Lagrangian, and really there's 3 types of up fields, there's 3 types of down fields, and 3 types of neutrinos, and 3 types of electrons. So implicit in this, if I take away the dot dot dot, is that those are matrices with a unit matrix in there. Okay, so they're diagonal. Okay, and the coupling is G over the square root of 8. That's actually that's why the weak interactions starts off with G2 squared over 8 mw squared minus J charged mu J dagger charged. So that's the beast that was called G Fermi over the square root of 2. Okay, so that's where that comes from, and that's where the the neutral sector is a little more difficult. So you have to write them out. The Lagrangian looks like the following. It starts at G3 W3 times the third component into left-handed current minus G1 B mu times a singlet current, and we write those W3s and B's in terms of W's and Z's. It turns into G1 cosine theta W A mu times the current that we'll call the electromagnetic current minus G2 over 2 cosine theta W, what we'll call the neutral current, Okay, and the electromagnetic current is what we always do it. Is the usual E bar gamma mu E with a minus sign plus 2/3 E bar gamma mu U. Okay. The Z current is, well, it starts off with U bar 1/2 gamma mu 1 plus gamma 5 U. Okay, so that's the original current, that's the B mu. I mean the W J3 mu, and then you mix in a piece proportionate to the sine squared of this weak angle with just a gamma mu. Okay. Then let's see. Let me not write everyone. I'll give you the general formula in a minute. I do want to write one though. The last one that comes here. So actually, let me write. Yeah, let me just write them all. D bar 1/2 gamma mu 1 plus gamma 5. That comes with a minus sign there, and it comes with a plus 2/3 sine squared theta W. This guy, the neutrino, is gamma mu 1/2 gamma mu 1 plus gamma 5 nu, so that has only the left-handed piece. And the electron also has something interesting in it. It's E bar, it's minus 1/2 gamma mu 1 plus gamma 5 plus 2 sine squared theta W E. The interesting piece here actually is that the vector component goes like, let me factor out a minus 1/2, 1 minus 4 times the sine squared of the Weinberg angle, or the weak mixing angle. In practice, this is very close to a quarter. So this vector current then is almost a cancellation. So the weak vector current for the electron is almost a cancellation, which is good. Good news. It's bad news. It's bad news if you try to measure it, it's small. But it's good news is that when you do measure it, you actually get a very accurate measure of the Weinberg angle. And this is something that Krishna Kumar is taking advantage of in his experiments. So it's worth pointing out that if you measure this small quantity, you get a very good measurement of the mixing angle. If you measured one of these others, you measure the vector current here, you have to subtract off 1/2, and so your relative error actually goes up. Okay, the general formula here is it's chi bar tau 3 gamma mu 1 plus gamma 5 minus 2q sine squared of the weak mixing angle. So all these features that I've just been writing out are tau 3 is either plus or minus a half, and the charges are just like that. Okay. So this is the origin of then the electric charge is T3 plus y over 2 that we used before. So that's just how the charges worked out given the normalization that we chose. It tells you that the electric charge, if you look up in there, the electric charge E is G1 cosine theta W. And the other thing that you can see working backwards is that for all the right-handed fields, Q is y over 2 for any right-handed field. So that was our hypercharge assignment that we had up there earlier. There. I think that's all I need to do on that guy. So I think I'm ready to leave. I want to go into the Yukawa couplings, which has a good deal of fun to it too. I think we've done everything we need to do here so far. So far we have all the interactions out. We have the masses out. We have the Higgs masses. The only thing I haven't focused on is the coupling of the Higgs to the W's, but we'll come back to that. Anything before we move on? Yeah.
So the weak Hamiltonian, you get that just by integrating out the W.
Yes.
Okay.
So basically, the weak Hamiltonian is, the first approximation is that diagram there, where we make our classic approximation that the propagator just goes like 1 over mw times the delta function. We'll do this a little bit fancier. We did a little bit already in our operator product expansion, but I want to do a little bit more on weak interactions later. Okay. So, anything else? Yes.
Is it possible to see how the left-handed and the right-handed electrons hypercharge without the differential?
Let's see. You want to work out how we get the electron charge to work out exactly. Okay. No, let's see if I can do it. The coupling was the electron had hypercharge -1, so the Lagrangian would be E bar. Actually, I'm pretty sure that's -1. Let me just look it up. E bar G1. This is left G1 B G1 over 2. I'm pretty sure. Left-handed electron is -1. The right-handed is -2. So it's actually minus here. minus G1 B mu over 2, and G2 tau 3 is minus 1, so there's the minus 1 over 2 Z mu, no, W3 mu E left, and it's E bar right minus G1 B mu, and the hypercharge is minus 2, so there's no over 2 there. Okay, so it's E right, E right. Okay, so we take B mu is cosine theta A mu plus it's minus sine theta Z mu, and W3 is sine theta A mu okay, so that's the mixing. I want to collect the A mu pieces, so I get minus G1 cosine theta W E bar right E right, and then I get G1 over 2 cosine theta W plus G2 sine theta W over 2 E bar left E left. Okay. Now, the tangent of the Weinberg angle, of this weak angle, is G1 over G2. So it says that G2 sine theta W is G1 cosine theta W, right? So these two guys are actually the same. So the half plus a half adds up to 1, and we get it. Good. So I get minus G1 cosine theta W A mu E bar right E right plus E bar left E left. Okay? So it worked. Okay. So anyway, so there's how it is. The feature that you see always is that this one's not going to get any piece that comes from W3 because it doesn't couple. So the right-handed couplings have no W3s. They just have G1 hypercharge B. B always turns into cosine theta A, so it's G1 cosine theta hypercharge over 2. So the right-handed piece, hypercharge over 2, had better equal charge. Because this is the only place where the photon couples to the right-handed piece. In the left-handed pieces, you have this complicated merging of those two. But you always get G1 cosine from this guy and G2 sine from here. G1 cosine, G1 sine are the same, so they add up. And they've been chosen to make it work out. Good. Anything else? All right. So, preliminary to the Yukawa coupling. This is just a little piece of math. This is, remember, phi is a doublet. It's special to SU2 is the fact that I define phi bar is I tau 2 phi star. It's also a doublet. Okay. Okay, now that's what I want to show you. This is special to SU2. Normally in if phi is a fundamental in SUN, then phi star goes like the n bar representation. But in SU2, one of the features is that the doublet bar is equal to the doublet. That wouldn't be the case if we had if this was SU3. Okay, so to show that we want phi goes to phi prime, which is u phi, and u is in e to the I alpha dot tau. Okay. Then phi bar will go to phi bar prime, which is, well, is I tau 2 u phi star. Yeah, and it's u star, of course. It's u phi start, which is, so let's do tau 2 u star tau 2 I tau 2 phi star. Okay. So I brought the I in. That's nothing much. Tau 2 squared. Let's put it downstairs just so it's not, you don't think it's squared. Tau 2 squared is 1. So that's the same thing, which is then tau 2 u star tau 2 phi bar. So if this is going to be a doublet also, we have to ask whether that's exactly equal to u. Okay. And so is it? So here we're going to use that tau 2, tau 1 star, tau 2. Well, tau 1 star is just tau 1. There's no real numbers in that. So that's tau 2, tau 1, tau 2 is minus tau 1. Tau 2 star, tau 2. Well, tau has an imaginary number in it, so when we complex conjugate it, it changes sign. So that's minus tau 2, tau 2, tau 2, just from the imaginary number. So that's also minus tau 2. And tau 2, tau 3 star, tau 2, just like tau 1, is minus tau 3. So these guys satisfy tau 2, tau star, tau 2 is minus tau. Okay. So then tau 2 e to the I alpha dot tau starred tau 2 is tau 2 e to the minus I alpha dot tau star tau 2, but then bringing the tau 2 through the tau, so each term in the Taylor expansion you just bring them through, converts it back to e to the I alpha dot tau equals u. Okay. So this is a doublet. You can see why this would fail in SU3. If I have SU3 and I've got 8 of these matrices here, it would work for the first 3, but then you come down somewhere later on, tau 2 doesn't anti-commute with, let's say, lambda 8, because lambda 8 has unit ones in there. So it would be this would be plus lambda 8 in SU3. I don't know if you can do that in your head. Do you know the SU3 matrices well? All right, let me just show you. Then, since I started there, in SU3, let's take one that lambda 8 is 1 over the square root of 3, 1, 1 minus 2. Okay, so it's 1 in the upper components. Lambda 3, or lambda 2 is tau 2, 0, 0, 0. So lambda 2, lambda 8 star, lambda 2, well, it equals the 1 over the square root of 3, 1, 1, 0 everywhere. It's not equal to lambda 8. So this procedure then doesn't work in SU3, and there's no way to make it work. So it's a fluke of SU2, if you want. I don't know if a good group theory reason why it works, but well, I'm sure I could come up with one, but there's the hands-on way to see how it works. Okay, so this then tells us that phi bar is a doublet. Phi bar is phi 0 bar minus phi minus. There's an extra minus sign around it. It's not a big deal in any of the story, but there is one there. It just comes from tau 2 being I and minus I on the off diagonals. Okay. The other place that you may be familiar with this, if you know some phenomenology, is you know that K plus and K0 form an SU2 doublet. You know that K0 and K minus form an SU2 doublet. They sit in a bigger octet, but those are both doublets. So the fact that they're both doublets is a reflection of this. One is like phi, K plus and K0. The other one is like this phi bars, K0 and K minus. So the math of having those be doublets is the exact same as the math that we just went through. Okay, that's pretty relevant for the Yukawa couplings because we need to use that. Okay. If we take the quark doublet, sorry, quark left-handed. So this is the form that looks like U and D left-handed. So actually, let me take that away. That's a doublet. I've multiplied it by a doublet there. There's a singlet. The hypercharge assignments here, this one had minus 2/3. That was the hypercharge assignment that we wrote down. The Higgs, we gave a hypercharge of +1. So if we can add something over here that has minus 1/3, then that will be hypercharge neutral. So that's allowed. Okay, you're only allowed to write out things that are invariant under the hypercharge transformation. Right? And if you look at the table of things, that can be a D right can sit there. Okay, you want to see? Jared, you're looking a little puzzled about the when I said the hypercharge assignment.
You meant by, what do you mean by neutral?
Okay, so let me actually explain that in a little more detail. Okay, so these guys, the hypercharge transformation is for example, D right goes to e to the minus I some angle over 3, where that's some phase rotation, the U1 rotation. At the same time, the psi quarks go to e to the, it's plus 2/3 I alpha psi quark, and phi goes to e to the I alpha with a 1. Okay, so the hypercharge rotation is always, the field psi goes to e to the I hypercharge assignment times the phase. Okay, this has to be an invariance, and so the hypercharge assignment of the phase that comes out of here has e to the I 2/3. The phase here has e to the I 1. Here is minus 1/3. For that to be an invariance of the overall system, these quantum numbers have to add up to 0. Okay, so that's what I meant by that. Okay, right? Yeah, good. So this hypercharge invariance, psi bar will then go like minus 2/3. We do that phase transformation on everybody, that overall ends up being an invariant then. And the way you check that out is just count quantum numbers. Okay. Okay. So another way to make it invariant, well, if I took the lepton doublet, the left-handed doublet there, this doublet there, that's an SU2 singlet, so that's a singlet now. I can add another singlet onto it. The hypercharge again is 1, 1. The right-handed electron has hypercharge minus 2, so that's also an allowed piece, allowed by the hypercharge assignments. So that coupling is okay. But we also had psi q left, phi bar is a doublet. So that also is an allowed SU2 singlet there. That's now a SU2 singlet. So okay, does everyone see the SU2 singlet part too? Okay, that's also on. Okay, if I do a transformation on this SU2 transformation, this goes to, let's do it up here. This goes to U psi, this one goes to U bar, because it's barred psi, so that's a singlet. But by contracting two doublets like that, I make that a singlet under SU2, and then by counting the hypercharges, I make it a singlet under U1. Okay, so these hypercharges here are, that's minus 2/3 again. Now it's minus 1. So 2/3. I can add a UR, which why is my math not adding up right? I see. Actually, I have a mistake up here. I can see it already. That was 2. This was 1. This is 1, and that works out. Okay. And the way I just caught it is, remember the thing I just said about the right-handed particles hypercharge assignment divided by 2 is the charge, and we just went through that. Okay, so this divided by 2 is the charge of the right-handed down. This divided by 2 is the charge on the right-handed up. All right. So that has to be a plus a third, minus a third there, and then it all works out. And the other one is, let me just change it. And then the other one that can work is the psi bar left, lepton, phi bar is a singlet, hypercharges 1, minus 1, so you have to have a 0 there, or new right is the allowable one there. Okay. So this tells us that we can write out all the following terms. The Lagrangian is, well, we can have psi bar q left bar phi down right. But there's a bunch of these guys. There's 3 of each type, so let me put an I there and a J there. And there's 3 generations of each. So I can write some gamma I J there, and I'll put a superscript D on it because the D right lives there. I have the gamma U I J, psi bar Q left I, phi bar U right J. I have gamma E, gamma nu, IJ, psi bar lepton left, phi E right, IJ, and gamma IJ for the neutrinos, psi bar lepton left, phi bar nu right J. Okay, everyone comfortable with all those terms? Lots of terms, yes.
Quickly again, what were the I and J for?
Okay. They were for, there's actually 3 types of down rights. You know, so they're going to turn into down right, B right, and strange right. The 3 minus a third charge quarks.
It's all the quarks.
It's all the quarks.
Okay, that's all.
This is all. So there's 3 doublets of quarks. There's 3 doublets of leptons. There's 3 neutrino rights, 3 electron rights.
So it's just summing over all the generation.
It's just summing over all the generations. That's right, exactly. But these are all these cross terms are allowed here. So you can. There's nothing symmetry-wise that forbids what you might want to call the top right to connect up to the doublet that has what you might think is the upright, up left. Okay. Okay. So these then of course turn into mass terms when we do the symmetry breaking. So phi goes to 1 over the square root of 2 v plus h downstairs. Phi bar goes into 1 over the square root of 2 v plus h up there and 0 downstairs because of the tau 2. And so you can sort of read off all the mass terms. Then psi bar q left phi down right equals, well, I just get the lower component here, which is the down component. So it equals 1 over the square root of 2 v plus h down left, down right. But if I took psi bar q left phi bar upright, that gives me the upper component because phi bar lives in the upper component. So that's 1 over the square root of 2 v plus h u bar right left u right. So these then turn into mass matrices. L equals, well, let's take minus 1 over the square root of 2 v plus h factored out, and then it turns into down left gamma down. I'm now making the indices, by putting the gamma inside it, I'm making the indices implicit. That's a 3 by 3 matrix there. This is left right plus the Hermitian conjugate. Let me just write it, one of them out. D bar right, gamma dagger, D left. And then the same thing for everything else. U bar gamma U left right plus Hermitian conjugate plus E bar gamma E plus Hermitian conjugate left right plus Hermitian conjugate plus nu bar left gamma nu right plus Hermitian conjugate. Okay. So these are 3 by 3 matrices. Next time we'll come back, we'll diagonalize them. There's a little trick to diagonalizing them, so it's worth going through. And we'll have our mass matrices, and then I'll move right into weak currents and some weak phenomenology. Okay. Does anybody have any questions about that before we move on? Okay, good.